All right, today we are going to talk about geometric dimensioning and tolerancing. Remember that GD&T is a system that uses methodologies and symbols to control product, form, profile, orientation, location, function, and runout. So we have more than just placement. There's a lot more going on in here. We have a list of symbols here that are on page 167 in your book. The first four symbols are flatness, straightness, circularity, and cylindricity. Now these are individual features, which means that they only relate to a single feature on a part. Let's start with flatness. Flatness controls the flatness of a surface in relation to its own perfect form, meaning that we want to know how flat a surface is. If you will look on your book on page 169, that this surface must be flat within 0.005 of the datum surface B, which is right here. Also notice it has a positional tolerance of 0.010. So the datum tolerance is telling you that this part must be within 5 thousandths flatness across the entire surface and still be within the 10 hundredths tolerance. Okay? The second symbol we have is straightness, which is represented by a straight line. A part must be straight within a given tolerance. In other words, it cannot move. It cannot look like a snake. It must remain straight versus that datum line. The third one, circularity, controls the form of a revolved surface in relation to its own perfect form by independent sections. So, when you look down the barrel of my pen, it is circular. But that tolerance for circularity means it only has to be circular at whatever datum point is given. If the datum point is right here, it must be circular within the tolerance right here, but not necessarily down here. The tolerance zone is given to you on page 172. It shows you a cross section where circularity matters. So as an interpretation of this, you have the part, nominal surface, and then you have the maximum radius all the way around. As long as the part is circular within there, you are in tolerance. Even though this does not look like a circle, it is within 0.005 tolerance range. So it is circular to 0.005. Remember, 0.005 is 5 thousandths. You can't even see 5 thousandths. So if you're looking down the lead of your pencil, it may be circular to 0.5 thousandths. Okay? The next one and the last one that we have that is an individual is cylindricity. Cylindricity means that you must be within a certain tolerance down the entire length of the round part, or the circular part that is. It goes to the entire surface. So instead of just being at a single datum point, you must be circular all the way around. Okay. Next up, we have perpendicularity, which means that it controls the orientation of a feature which is nominally perpendicular to a primary datum or datum reference plane. In English, we have two parts crossed like this. It is nominally perpendicular. And to be perpendicular, we must be what angle? 90 degrees. What if I'm at 89 degrees? If that's within tolerance, we are still nominally perpendicular because we're in tolerance. Say the tolerance is plus or minus 1 degree, 89 to 91. We are still considered perpendicular. Okay? Next on our chart is orientation. Another orientation one is angularity. It controls orientation of a feature at a specific angle in relation to the primary datum of its datum reference zone. So you have seen tolerances prior to now about angles, right? And it shows that it must be, say, 15-degree angles. What the difference is with this symbol is it must stay at 15 degrees no matter if there's any changes in it at all. Okay? Next one, parallelism. Controls orientation of feature which is nominally parallel to the primary datum of reference frame. Okay? Now we go to some locational tolerances. Position. Controls the location or orientation of a feature in relation to its datum reference plane. Which means, let me find my example. Okay, this one shows location. In this one, our location of the 1-inch diameter hole that has a plus or minus size variation, 0.005 is allowable tolerance for the hole. Our locational tolerance is also 0.003 at maximum material condition in reference to datum A and B. So what that means is we can determine the exact zone of this hole and the exact size of this hole off of these two datums with this information. We don't figure that in here, so I'm not going to go too much into depth to it because there's a lot of math involved. I just want you to understand that this tolerance symbol means positional tolerance out of the diameter by 0.003 at maximum material condition off of datum A and datum B. You need to understand what you see in the box. Not necessarily how you interpret it, but what the symbology of it means, okay? All right. Where was I? We did location. I'm sorry, that's location position. Then we have location concentricity. Controls the concentricity of a surface or a revolution to a central datum. Remember when we talked about concentric circles? We have two circles with the same center point. This is the same thing with a rod, right? You can move forward or aft or in or out as long as you're in that same concentric circle. Next we have location. Controls the symmetry of two surfaces along the central datum. Then we have run out. This controls circularity and coaxiality of each circular segment of a surface independently about a coaxial datum. Machinists, you'll have to worry about that. Everybody else, you're okay. And then we have total run out, which is this one. Okay? I suppose the two we skipped. Should cover the ones that we skipped. Profile of a line. This is profile of a surface. Okay? You need to be aware of the symbology and what it means. That is the basic point of this. So
H you said was of a line.
It's a profile of a line. Correct. Okay?
And the other one was a profile of circle.
Profile of surface.
Surface. Sorry.
No problem. Okay, very good.
Oh, it is right there. Gosh darn it, I thought it wasn't in there. Never mind.
Okay. So let's identify. Using this example, let's identify. We can see from this is a leader line. It says this diameter, 0th line third diameter, is 0.500, half an inch, with a plus or minus tolerance of 0.005. We have a datum control of location of the diameter by 0.003 at maximum material condition, that's what the M with the circle is, off of datums B, A, and C. So this has three datum planes that we have to meet to make up this. And looking at this, since we have diameter and diameter, you should be able to tell me that that is a cylinder. Okay? Not too tough. On this one, perpendicularity. We know that off of datum A, the diameter must be 0.005 with it off of 9 degrees, plus or minus. On this example, what does this tell us? It must be flat. It must be how flat? Within 0.005 across the entire surface, and it cannot exceed 0.570 to 0.550 because of the plus or minus height tolerance. You understand? This does not override, this complements this. Okay, very good. That's enough of those. Let's move on to another topic. With fasteners, I'm not sure if you can read these or not, but the diameter, the hard call out of this first pin is 0.5003 to 0.4997. The hole that it's going into is 0.5009 to 0.500. So, would that be a clearance fit, a transition fit, or an interference fit? It would be a clearance fit because the pin is going to, I'm sorry, I said that wrong. It's a transition fit because if the hole is as big as it could be, 0.5009, and the pin's as big as it could be, it would do what? It would fall in because the hole is bigger than the pin. But if the hole was as small as it could be at 0.5000 and the pin was at 0.5003, the pin would then be bigger than the hole, would it not? So in the middle, this pin could fit in loosely, this pin could fit in tightly, depending on the size of the pin versus the size of the hole. Now the second one, B here, the smallest the hole could be is what? 7.50. The largest it can be is 7.53. The biggest the pin can be is 7.47. Therefore, the pin at its maximum size should still fall directly into the hole. Does that make sense to you? Because the hole will always be just a little bit bigger than the pin. And then finally, an interference fit, the hole at its biggest size is 0.5007. The pin at its smallest size is 0.5012. Therefore, the pin will always be bigger than the hole. That's called an interference fit. You have to drive that pin in. Okay? All right.
Is that in the book also?
I'm sorry?
Is that in the book also?
Yes, it should be. Moving on, I have a couple other things I want to cover on this. Nope, not in there, I don't. Okay, shut off.